Exercise 1827 is, again, just trying to see how well you're able to interpret the signals coming from aromatic molecules like benzene in spectroscopy, so IR spectroscopy and NMR spectroscopy. They give you the molecular formula, and you'd get that by doing mass spectrometry. You'd compare the molecular ion peak with the M+1 peak, and based on the relative heights between those, you can tell how many carbons you have, and then you'd also know the mass, the molar mass of the whole compound, and so you can use that information to figure out the molecular formula. So in this case, they're giving that to you. They've already done the mass spectrometry for you on the sample, and the other information they're giving you is, and I'll do these in different colors. You've got the IR spectroscopy in yellow, and then the NMR spectroscopy, which I will put in purple. Now we have two. We have H1 NMR spectroscopy, so just the H1 NMR, but then they also give us another type of NMR, the carbon-13 NMR. So those are sort of the three different types of spectroscopy that they're giving us, in addition to the molecular formula that they would have gotten for mass spectrometry. So the first thing you'd usually do to analyze this compound, to try to figure out what it looks like, is to calculate the index of hydrogen deficiency. How many degrees of unsaturation, how many rings or pi bonds are in the molecule? And the formula for that is 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of halogens. So fluorine, chlorine, bromine, or iodine. And in this molecule, we have 8 carbons, and so that's 16 plus 2. We don't have any nitrogens. We have 10 hydrogens, and we don't have any halogens. So that's going to be 1/2 18 minus 10. That's 1/2 of 8, which is 4. So we have 4 degrees of unsaturation. If you ever have 4 degrees of unsaturation or more, chances are that you have a benzene ring. So already the benzene ring is in the back of our mind. Now, because you only have 4, all 4 of those degrees of unsaturation are taken into account by the benzene ring. You have 1 from the ring itself, and then 2, 3, 4, 1 from each of those pi bonds. So that's a total of 4 degrees of unsaturation. That takes care of all of them just with the benzene ring. So outside of the benzene ring, we won't have any other rings. We won't have any other pi bonds. Now, you would want to confirm that you do have a benzene ring. So far, this is just a suspicion. And the way you confirm it is by looking at the IR signals and the NMR signals. As we discussed in the video for 1826, you have these common signals that you get when you do IR spectroscopy on benzene, that's on the top here, and when you do NMR spectroscopy on benzene. And just for the sake of contrast, note that 1650 is the upper limit for this carbon-to-carbon bond in benzene. If you have something higher than that, it's probably a carbonyl. So in this compound, we're thinking we might have a benzene ring because of the high degree of unsaturation. And if you look at the IR spectrum, we have a whole bunch of signals that are above 3000, that are around 3100. In fact, all of these first 4 signals are above 3000. Remember that when you get an IR spectrum, you want to draw 2 vertical lines. One at 1500, anything to the right of 1500 is the fingerprint region. It's all the single bonds in the molecule that sort of overlap with each other and give a messy signal, but one that's unique to the molecule. And then you want to draw another one at around 3000, and usually the bonds to the right of the absorption to the right of 3000 is an sp3 carbon to hydrogen bond. All those bonds absorbing energy, light energy. But to the left of 3000, those are these sp2 to hydrogen, sp2 hybridized carbon to hydrogen bonds. And so that's what we're getting there. And the way this would really look is like a messy peak, sort of to the left of 3000 on an IR spectrum, because they're really close together. So that is a confirmation of our benzene. And the other signal, the 1608, that is another confirmation of benzene. That's between 1450 and 1650. Those are the carbon-to-carbon bonds in benzene. If vibrating in new ways when they absorb that energy of light. So we have confirmation. All of these just confirm, all of those IR signals just confirm we have benzene. So much for the IR. Now, with IR is giving you information not just about what's there, but also about what's not there. Notice you don't have any signals for a carbonyl, you don't have any signals for an amine, you don't have any signals for any other functional groups. So just the benzene. Then if you look at the H1 NMR spectrum, we have further confirmation of the benzene. We have a signal for H1 NMR, for proton NMR, we have a signal between 6.5 and 8 parts per million. We have it at 7.1. So that's yet another confirmation that we have benzene in the molecule. And if you notice, the integration for that is 4. We only have 4 hydrogens on the benzene, which means we have 2 branches on the benzene. Because benzene all by itself has 6 hydrogens, the only way you can get 4 is by taking 2 away and replacing them with branches. So we have 2 branches. The thing, though, is you can have 2 branches on benzene in 3 different ways. You can either have them ortho, you could have them meta. So ortho is 1, 2, meta is 1, 3. Or you could have them para. And that would be 1, 4. So that's what we have so far. We know we have a benzene with 2 branches. We're not really sure whether it's ortho, meta, or para. Okay. They give us 2 other sort of pieces of information. They give us another signal in the H1 NMR. Now the signal is at 2.2, and it has 6 hydrogens in it. Now notice the benzene ring has 6 carbons. We only have 1 other signal, and we only have 2 more carbons. We have 8 carbons total. We have 2 more carbons in this 1 signal and 6 hydrogens to fit on them. The only way to do that, to have 2 carbons with 6 hydrogens, is 2 methyl groups. If you connect them in any other way, you won't have room for the 6 hydrogens. So we have 2 methyl groups. And the fact that both of these methyl groups, so that gives us our 6 hydrogens, the fact that both of these methyl groups, so that gives us our 6 hydrogens on just 2 carbons that we have left, because that's an 8 there, we have 8 carbons, and we've already used 6 for the ring, so we have only 2 left. They have to represent 6 hydrogens, that means 3 each. So the only way that both of these carbons can be represented in 1 signal is if there's symmetry in the molecule. Now that doesn't necessarily help us a lot, because there is a line of symmetry in all 3 of these. There's a line of symmetry in the ortho, down the middle there, in the meta, down there, and in the para, along the lines of the bonds. So there's a line of symmetry in each of these, so that doesn't really narrow things down. And also, these would be in a singlet. Well, that makes sense. It makes sense that they'd be in a singlet because if you attach these to the benzene ring, this carbon that they're attached to doesn't have any hydrogens on it. So in each of those cases, there will be no hydrogens next door, and so it won't split at all. It'll just be a singlet. Okay, so this is where we're at. We have a di-substituted benzene, and both of the branches are methyl groups. And to tell these apart, you'd want to use the carbon-13 NMR spectra information, this blue stuff at the bottom here. Now, the hardest type of NMR spectroscopy to interpret is hydrogen, because not only do you have the different number of signals and the different shifts, but you have the splitting patterns: doublet, triplet, quartet, quintet, sextet, septet, multiplet. With carbon-13 NMR, you don't have those splitting patterns. You just have the different numbers of signals. And so the information you get from it, it's easier to read, the information you get from it, but it also kind of gives you less information. The information you get usually from carbon-13 NMR is the number of different electronic environments that a carbon is in. So here we have how many signals in this carbon-13 NMR? We have 1, 2, 3, 4 separate signals. So that means we have carbons in 4 different electronic environments. Okay, now let's draw each of the possible molecules we have and see how many different electronic environments we have carbons in. So let's say it's ortho, so ortho-dimethylbenzene, or meta-dimethylbenzene, or para-dimethylbenzene. So those are our 3 possible molecules. We have to choose between them using the information from the carbon-13 NMR. Okay, I'm going to draw in the lines of symmetry. Go through these one at a time. If it's ortho, how many carbons do we have in different electronic environments? Well, we have the methyl group carbon. Those 2 are in the same electronic environment. We have the carbon they're attached to on the benzene ring. Those are both in the same electronic environment. We have the carbon that's one further away from the methyl group. Those are both in the same electronic environment. And we have a carbon that's 2 away from the methyl group. Those are both in the same electronic environment. And so that gives us a total of 1, 2, 3, 4. That gives us 4 signals in a carbon-13 NMR spectrum, because we have carbons in 4 different electronic environments. Compare what happens if we do that same thing for meta-dimethylbenzene. So we have our line of symmetry down here. You would have a carbon in between the 2 methyl groups, that's 1 electronic environment. You would have the carbons in the methyl groups, that's a 2nd electronic environment. They're in the same electronic environment though, because they're on opposite sides of the line of symmetry. You have the carbon they're attached to, that's a 3rd electronic environment. You have a carbon that's 1 away from them, there's a 4th electronic environment, and then you have the carbon on the very end, which is a 5th electronic environment. So if you were to count up all the electronic environments for carbons in this molecule, you'd have 1, 2, 3, 4, 5. You have carbons in 5 different electronic environments. That would give you 5 signals in a carbon-13 NMR spectrum. Okay, let's think about this last one, para-dimethylbenzene. We have our line of symmetry here. In this case, we have the carbons in the methyl groups. So that's 1 electronic environment. We have, and also, let me draw the other line of symmetry here. We have a line of symmetry going through the other end of the molecule. So that makes those 2 carbons the same. Then you have the carbon they're attached to. Those are on opposite sides of that line of symmetry, so those are in the same environment. And then you have the carbon that's 1 away from them. Now notice, oops. So notice that carbon in purple is 1 carbon away from the carbon in the methyl group, just like the one across from it. And notice the one on the other side is also 1 carbon away from a carbon in a methyl group. So they're the same distance away from the same things. So they're all in the same electronic environment. So in that one, you'd only have 1, 2, 3. Oops. 1, 2, 3 different electronic environments for the carbons. The carbon in the methyl group, the carbon attached to the methyl group, and the carbon that's one atom away from the carbon attached to the methyl group. So you'd only have 3 different electronic environments. You'd have 3 signals in a carbon-13 NMR spectrum. Okay, so if we go back, what they gave us were carbons in 4 different electronic environments. We have 4 signals, 1, 2, 3, and 4. So it can't be para, it can't be meta, it has to be ortho. So we figured out that we had a benzene ring based on the IR information, and also based on the NMR, the proton NMR information. Based on the integration for the protein NMR, we knew that it had 2 branches, so that narrowed it down to the ortho-meta-para. Looking at the atoms that were left, we had 2 carbons, 6 hydrogens. There was only one other signal with 6 hydrogens in it. The only way to have 6 hydrogens in one signal is to have, on 2 carbons, is to have 2 methyl groups. So those were our branches. We drew the 3 possible molecules, saw the number of signals they would give us in a carbon-13 NMR, and compared that with the number of signals they gave us. Because they gave us 4, the answer has to be the molecule that only gives you 4 signals in the carbon-13 NMR. And so the structure of the molecule is ortho dimethylbenzene.